to the course on FPGA based signal processing systems. In the previous lecture, we had learned discrete Fourier transform. What are the outcome of the discrete Fourier transform? Those are the frequency components which are present in that. If you take an endpoint DFT, frequency components, and what is its magnitude and phase in the original signal. So taking the endpoint DFT, the equation which we had used in the previous lecture, where capital N shows the number of samples in the signal which you take for the DFT, or the window length. K is the bin index, where small n indicates the instance of the samples which are arriving, which are considered here are mainly 0 to n minus 1, and the K is a bin index which varies from 0 to n minus 1 as well. So in case of DFT, we had also looked into the shifted DFT. If we know the xk or x of k of the signal, or the k varying from 0 to n minus 1, and the shifted DFT can be obtained by, that is, if the time shifted signal, in that case what would be the DFT of the time shifted signal. So if you in the frequency, it is e power j 2 pi k n by n, the shifting property is applicable to the endpoint DFT. So when using this, we had also took an example of x of n, the signal, and the x of n plus 3, which is here left shifted. So we found that x of 1, the kth bin, that is the first bin, fundamental bin, resulting for e power minus j pi by 2 in the example which we took in the previous lecture. Now the shifted one, if this is for the shifted case, what is the fundamental DFT of the fundamental one? E power j 2 pi k, n is here 3 samples shifted. So we can see this 3 samples shifted over here. So 3, n equal to n is become 3 here, and computing the shifted DFT for the using the unshifted one, the x of n. So we get 4 e power j pi by 4. So that is multiplying this with the factor with this e power j 2 pi 3 by 8, resulting in the phase change, not the magnitude change. There is a phase change of from minus pi by 2 to 45. So the shifting causes the phase change in this. Moreover, in the DFT, we compute all the bin indexes from k is varying from 0 to n minus 1. Suppose I want to know about only the fundamental, when what is the signal and what is the magnitude and phase of this fundamental in this particular signal. If I do a DFT, then DFT computes all the kth bins. So instead of that, can I use only not varying k from 0 to n minus 1. I'm interested in only one particular harmonic or fundamental, one alone in the signal. So k equal to 1, or k is 2 alone, second harmonic, third harmonic, and fourth harmonic, and so on. If that is the case, I need not compute this x of k for all the bin indices using the equation, the summation equation. I would be happy with only having one k value of the signal, and I want to extract that particular signal instantaneously from the input signal. The fundamental alone I would like to extract. So in that case, what would be the effective mechanism, or how can I extract? Is there any filter to it, or DFT can be used as the used for that purpose. Here is the sliding DFT. So with this background, let us take the signal which is having the it is shown here, and it has a fundamental, and it is having also added a second harmonic to it. This can be with fundamental, second harmonic, third harmonic, and noise as well. So in this case, the samples are shown for here 32 samples, but one period takes 16 samples. Okay, so from here 0 to 15 samples, and the amplitude here is a sample. So n is 16, we consider that capital N, so 16 point DFT we have to take. So considering this from the first, what SDFT does here, sliding DFT. First consider at the 0th bin, zeroth time instant, or zeroth bin indicates the DC component, first bin indicates fundamental, K2 is second harmonic, and so on. So when we are trying to extract this from the signal, what we are trying to suppose extract this fundamental alone. It has fundamental and second harmonic. I just took for the example to show k equal to 1 in the bin index in the DFT equation. If we put k equal to 1, we can extract the fundamental alone. So how we are going to do that? So 0th instant, if we consider at the 0th instant, so the samples minus 15 to here, that is 0, needs to be taken in a window and then compute the DFT. After that, slide it once, 14 to 1 samples, compute the DFT, and then one sliding advance, that is right hand side, minus 13 to 2, take the samples of minus 13 up to 2, okay, plus 2, okay. So this is 16 samples, again this is 16 samples, minus 13 to 2, again 16 samples here, including 0, minus 12 to 3, and so on. So we can compute the DFT of each, so that instantaneously at 0th instant, what is the DFT value, magnitude and phase. Similarly, first instant, what is the magnitude and phase, second instant, third instant, and so on. So we need to know the negative instances of the signal as well. So minus 15 to 0. So I did not know at when I am standing at the 0th instant, and here in this signal all of them are 0. So at 0 you get some value 1, these values you will get magnitude and phase, and so on. When I come to the 15th instant here, okay, 0, 1, 2, 3, that means 16th sample over here. So it takes 0 to 15 samples. So now I got all the samples at the 15th instant and take the DFT. While doing this, you can say that the 0th instant to 15th 0 to 15 samples. So the window, which is the rectangular window here, assumes 0 to 15 samples and take the DFT, and then slide it once. So take this 1 to 16 sample and then compute the DFT. In this, when we try to compute this DFT, you can see that the sample which is going out and the sample which is coming into the current window, right, so are same. So in a periodic signal, this is the case, that where whatever the sample which is going out and the sample which is coming in is same. Okay, so similarly, if you slide it once, again the sample which goes out and the sample which comes in are the same here, the periodic one. So here we have so what are the overlapping cases? So if you see in the first window, from 0 to 15, and second window 1 to 16. So the common samples are 1 to here up to 15. Okay, the 16th sample is added and the 0th sample is subtracted in the current window compared to the previous window. So instead of computing this DFT for one window and then second window, third window, fourth window, fifth window, and so on, so why don't we use the previous instant DFT to compute the current instant DFT? So that's how the recursive equation has begun here by using this property. So when I am in current window, I make use of the previous window DFT and subtract the sample which was there and add the sample which is coming in. Okay, so this can happen only when you have this full cycle. We take this. So considering this is the next window, and then it moves on in the particular direction. So after with this one, so we can write this equation of the DFT. Here x and k, that is the current window DFT, current instant DFT. N is the instant we mentioned. Usually when we take DFT, we just simply say x of k, that is the frequency bin index. So here because the instant is involved, so we put the suffix in it, x suffix n k, and one sample is advanced or the delayed here. So the e power j 2 pi k by n, that n as big small n, or the number of shift is only one sample. In our previous example, we took 3, so that is becoming 1. So the phase should be adjusted this much, e power j 2 pi k for the next one. And then x of n minus k, this is the previous instant DFT, and I add the 16th sample and subtract the 0th sample. So this is how the current instant DFT can be obtained. So this is called the sliding DFT. When this number is going to be a complex number, x suffix n k, but I get every instant after first accumulating the n samples, which sample we are supposed to be there, and after collecting that sample you would get the output at that sample itself. So the x suffix n k, and which is having the complex number. If you take this is going to be x plus jy in this instant n, and then next instant n plus 1 x plus jy 1, and similarly for all other instances, if you take x and y, or its magnitude and its phase separately, or we can plot the magnitude and phase also instantaneous, or we can take the real x, all x's instant wise, and then all y's in instant wise, and we can plot him so that we get the real and imaginary points. So the real sequence and the imaginary sequence represents the in phase and quadrature components of the signal, which was the fundamental or second harmonic or the third harmonic, which you had chosen as k equal to 1 in the bin, as a bin index. So here, taking this samples, so what would be the transient response of this filter, considering this k is tunable 0, 1, 2, 3. I can make it as I can extract fundamental alone from the signal instantaneously, 1, 2, 3 and so on. In that case, the transient response of it is n minus 1 samples. So I need to wait up to n minus 1 samples get collected, that is 0 to n minus 1, 15 here, and then I get the instant at that instant DFT. So up to this point, what the DFT is computed depends on the garbage, the values which were initially there. So once I get these points, and then I start getting the instantaneous values. So you have to wait one cycle for it to get the correct output of the fundamental or the second harmonic which is required. So the transient response of this SDFT, as looking at as a filter or the system in the discrete domain, it is n minus 1 samples. So how we get this recursive equation now? So taking the endpoint DFT equation, that is n is varying from 0 to n minus 1 summation, x of n is the sample which we are going to consider, that is 0 to 15, e power minus j 2 pi k n by n. So k is varying from 0 to n minus 1. So here we are not going to vary the k from 0 to n minus 1 in our SDFT. We are interested in only any one of 0 or 1, 2, 3, or multiple ones, multiple SDFTs needs to be taken. So x suffix n k, which can be for the nth instant, can be written like x suffix q plus m, where m is varying from 0 to m minus 1 in summation. So that we are just trying to get the recursive equation of this sliding DFT. E power minus j 2 pi k n I just replaced with m, so this notation will be useful, and when we come back to the n again. Km by m. So m is again, it's the same meaning, it has the number of samples you are considering in the window. So this is for the current window. So what is this q and m? Okay, so the x of k, you can notice that DFT and the SDFT, we have the instant specified here. The k carries the same meaning as the bin index. So q equal to here n minus m plus 1. Okay, so this n represents the instant in which you are computing the DFT, and m is the number of samples in the window, minus 1. So here, so whereas this w can be replaced with e power j 2 pi m, can be considered as a Tudel factor here, j into 2 pi by m, that is e power j 2 pi by m as the Tudel factor, and we can replace this complex term with this wm for simplicity. So k this is valid for k varying from 0 to m minus 1. So if this is in our case, if suppose you are computing the n equal to 15th instant, so 15 and the m is here, what is the m? We have taken as 16 samples plus 1. So this would result in 0. So here q becomes 0. So x of 0 plus m, which is summation, m is varying from 0 to m minus 1, e power minus j 2 pi k, suppose considering maybe 1 also, km by 16. Okay, so how many samples from this is 0 to 16 minus 1, 15. So x of 0, and then this is plus x of 1 into e power minus j 2 pi k into this is 1 by 16, and so on. It goes up to x 15 e power minus j 2 pi k considered to be the which bin index you are interested in, and m here is this m is going to be m minus 1, that is 16 minus 1 up to 15. So we considered 0 to 15 samples for this DFT. So if I make this here, this is for the case of nth instant. We just may replace this minus k m by n. So now considering this at the n minus 1th instant, so what would be the previous case, previous window samples? If I consider the current sample is 0 to 15, previous window should be minus 1 to here, so 0 to 15 sample, minus 1 to at least 14 sample, 14 including 0. So here is the samples which needs to be 0, 1, 2, 3 up to here 15 plus 1, 16 samples needs to be here in the previous window. So this Q holds true for the same cases. This would be giving the DFT of this previous window, and current window is 0 to 15. Okay, so there is a overlap from 0 to 14, yes, with respect to the previous window, and I subtract this sample and add this sample in the current window, so that we can have the using the previous instant DFT you can get the present instant DFT. So to do so, here xn suffix nk equal to m is varying from m minus 1 to this wm k m minus 1. So we take this and then added the, this is subtracting the previous instant and adding the one which is nth sample which is coming in. So these two terms related to the terms which are going out and the sample which is coming into the window. So from this q minus 1 nth instant DFT can be found, that is the current window 0 to 15 can be found by using the previous instant DFT and subtracting this, and further simplification results in the summation here wmk minus 1. So mk is a simplification, here is this wmk and q minus 1 km, and this one becomes 1 here. So this is wm minus k minus in plus mk, so that would be equal to, here I have, yeah, w suffix m minus k m by m. So this is going to be, and the rest of the terms, if we take the w suffix m minus k, instead of that we take this m and minus into minus this plus k if we take out. So you have this term here with a q plus m minus 1 and q minus 1 and mk already, and this mk would be here again simplified to 1, right? This is km would be 1, so this will be 1. Okay. So here this is fine, okay, minus k m the first term, which can be m minus km into w suffix m plus k. Okay, so this is going to be this term and here is this term. Okay, so this is going to be the 1, and when we simplify that, the w suffix mk, the total factor, and if we take this one completely, going to be wn minus 1k, and we have the, so this xq minus 1 and the term which is taken out here, so you have minus q minus 1, and this term also is taken common, we get this. So xn minus 1, if you take this q term in terms of q equal to n minus m plus 1, so substituting them we get here, subtracting this n, this becomes n minus m and this becomes n xn. So yes, the current instant DFT can be computed with previous instant DFT, subtracting one sample and adding the other sample, and then having this xmk, which is adjusting the phase shift e power j 2 pi by m, that is power k. For k depends on the k, it would vary, and only one sample we are varying, so this is the phase shift parameter. So this equation is corresponding to the sliding DFT equation. So with this, taking this equation, and I've just replaced those m's with the n's. Now to coming to this point, so we have the 0 to 15 samples in the first window, and then the other one from 1 to, and slide it and get it. So the factor which is added over here R, which is called the damping factor. If the damping factor is the damping factor we use to have the stability of the output what we get, because if we take this as at y, I'll tell you maybe in the next slide how this R is going to be helpful in stabilizing this system, this discrete system. So if we take the transfer function first, so taking the z transform of it, this n, so we have 1 minus r power n z power minus n, this term 1 and 2, collecting them, r e power j 2 pi k into this also, and we have the 1 minus r power e power j theta k z minus 1, so which is corresponding to y by x. Y is the output here, output is these two terms, and these are the inputs. Okay, so we get theta k equal to 2 pi k by n, where this is simplified here, this is going to be theta k, and that's why e power j theta k, theta suffix k we have written, that is k is taken as suffix here, theta is 2 pi k by n. So we can have the xk whose z transform, suppose this is, and here the multiplication r e power j theta k and z power minus 1 x of z, plus this is small x, we can consider this as input. I take x in z into, that is also r e power j theta k minus r power n into this one input, again e power j theta k into z power minus n x in z. Okay, so adding this two would result in here here, bringing this side and making the transforms y by z, the transfer function results in z minus 1, you can see this term, and this term would give you 1 minus r power n in z power minus n into e power j theta k. So for, taking the z transform of it, we'd get h SDFT. So this has, if we look at the pole zero configuration of this particular filter, so we have one complex pole here at the bottom, and there are n zeros on the numerator, which represents this polynomial as n zeros. So we take this z transform and separate them to real and imaginary parts, because this has the real of z plus imaginary of z. So here you have the j x plus jy, for example. So this x plus jy, so we take this real and imaginary, so take it e power j theta k as a cos theta k plus j sin theta k. Similarly here, and separate the real and imaginary parts, you would get this is a factor which is to be multiplied. If you recall that the DFT, to get the original magnitude for all the k bins, the 2 by n valid is valid. For DC bin it is 1 by n to be multiplied, so that's the factor here. So 1 minus r power n z power minus n and r cos theta k minus r square z power minus 1. So we get this form for the real and imaginary. This is a transfer function again. So this will be 1 by n for DC and k equal to 1, this factor. This will be 1 by n for the factor. So now taking the real and imaginary part from the transfer function. So we have drawn the diagram of the equation. So this is x of n. You have the 1 minus z power minus n, that is a comb filter, and the rest of them here, this equation, this part with 1 by 1 minus r cos theta k z power minus 1 r square z power minus 2, which results in the resonator. This is the one, that is, you can have seen this. This is the resonator r cos theta k, two delays, one is r square here, this is resonator, and this r cos theta k and r sin theta k r square, this comes from the here. that is from r cos theta k minus r square z minus 1 to get the real part, and here the real or in phase component, and this is imaginary or the quadrature phase component. So here this is multiplied r sin theta k, and this factor is valid for, as I said, this factor k for all harmonics for the real sequence. Anyway, this is, and it will be 1 by n for the case of DC, k equal to 0. So this theta is 2 pi k by n here, that is theta k. So this is the kth bin, we have shown this, and that is something fsk is specified, that is the sampling frequency. If you simulate it in the MATLAB or use this, what should be, how, when this delay should be used, what is that n or n minus 1. So this delay corresponds to what, how much time. Okay, so that is decided by fs, the sampling frequency. So fs can be taken, what is the frequency you are interested in, into number of samples in the periodic, that signal which you consider, or endpoint DFT you consider. So fix this fs as f into n if k equal to 1. K equal to 2, then again k will be according to k into f into n needs to be made for k only 1 bit. So this gives out in phase component from the signal, if the signal contains fundamental, first, second, third harmonic and noise. So this noisy signal can be passed on to this filter and get the in phase and quadrature component. Here you will get the sinusoidal, and here you will have the cos, that is minus cos, actually you get the minus cos here. So we will see the pole 0 diagram of this. You have this is the unit circle, the one in orange, and you can look at this r, the damping factor, which is actually, if r is not in r equal to 1, all the poles and zeros, this one complex pole and the n zeros corresponding to 16 here, n is 16, we have placed n 16 for k equal to 1. So 2 pi by n, which is k is 1 considered, so this is at angle theta in which equidistant zeros are placed, and the pole 0 is cancelled by a pole, it depends on k you choose. So if k equal to 0, this 0, then this 0 will be cancelled by the pole. If k equal to 1, this particular 0 is cancelled by pole, and if k equal to 2, this will be cancelled, and so on. So the zeros exhibit the magnitude response as zeros. If you recall the comb filter, what we did in the filter designs, FER filter, and then when k equal to 1, this is cancelling out. So the poles, because of the cancellation of 0 and poles, the magnitude response will be peak here due to the pole, and other instances it will be 0. So if you take the frequency response of h of e power j omega here, so this would be a fundamental here, that is this is here the peak response, and then it starts decreasing. This zeros gives the response as 0, and in between, if it is cancelling, this is the location at which, suppose for the 50 hertz, this 50 hertz would be taken magnitude 1 or 0 dB, and at second harmonic the other, this pole, this 0 would be, so it is giving 0 response, and then this will be at third and fourth, fifth 0 locations. In between, these frequencies will be passed with attenuation. Okay, so we can cancel any of the zeros which according to the k you choose. Fundamental, we choose this. If you want a DC alone from this, you can have this. You choose the k equal to 0, so that it cancels out this this 0 by a pole, and get the peak response. Only you can extract DC from that signal. So all the cases, the transient response is n minus 1 samples. This gives the pole 0 diagram of the SDFT, and this R specifically damping factor, if the zeros are placed over the unit circle and the pole which is cancelling the 0 on the unit circle, then there will be a chances of here this gets unstable. So that will be marginally stable, and slight change in the noise or anything, that accumulation of the error, virulent effects and all those things would push the pole outside the unit circle. So this system will become unstable. Instead of giving the fundamental signal, the instantaneous signal, it won't stabilize, it would start growing if it is slightly pushing away from unit circle. So the factor R needs to be introduced in the transfer function or in the recursive equation. so that this 0 and pole are slightly pushed inside the unit circle, okay, and to make it stable. So R is close to 1. Okay, so this R needs to be chosen as close to 1, 0.998 or 998.87 and so on. So this would, so that there won't be much error in the extracted signal magnitude as well. So this is the significance of the adding R. So this system will become unstable because if we don't introduce the R. So the simulated diagram of the SDFT in Simulink, so is sinusoidal signal and second harmonic taken as, for example, 50 hertz, and this is 100 hertz, and we have few the amplitude of 1 by 2 I have added. This is 1 and doesn't have phase shift anyway. It can be added as well, and you can add noise as also. So this gives taken n as 64 samples for this, and the Fs is f into n, that is 50 into 64. This is the sampling frequency used in this design. So this is a comb filter which is realized, and we have the resonator over here, resonator. So this becomes 2 cos theta k, and then the part of this which is given in the transfer function as well as in the diagram. And to take the in phase component, and here is the quadrature phase component, in phase and quadrature. Quadrature phase component can be obtained from this. You can notice this 2 by n multiplied by to get the signal original signal amplitude from the DFT. So let's see the output now. Here the scope gives the amplitude and time. You can see this is the signal which has been taken, the input signal x of n. Okay, you can see the sample, the blue one, and the up to this sample n minus 1, okay, 0 to n minus 1, you can see the transient response of the filter, which is not the, this is chosen for k equal to 1, fundamental to extract fundamental. Up to this it is giving the, you can see the pink one and also the orange one, the both of them. So here is the sinusoidal signal, and this is quadrature signal. So you have in phase and quadrature component taken out from the SDFT. So you can plot it instantaneously. After n minus 1 samples, you get the instantaneous output of the fundamental itself. You can vary this also k up to n by 2, and when we vary increase k, that is the sample number of samples. If you fix the Fs same, then number of samples per cycle would reduce, depends on the number of k, that should be considered. Otherwise, there are mechanisms to increase Fs and then keep the number of samples constant in over all the cycles. So this is the just simple extraction of the original signal present in the, this is a signal in phase component is already there. The quadrature component is actually the one more addition of the SDFT. You can get the quadrature component as well if you would like to use it in some other applications. So this is SDFT output. If we come to the modulated sliding DFT, so the factor R, which I have shown in the pole zero diagram, which giving the stability. So that R can be chosen so that it should be stable. But if the time increases, if you keep increasing this, the resonator output may have the oscillations to grow. So to avoid such instability problems in the SDFT, there is a modulated SDFT has been introduced. So taking the SDFT equation, that is x of 6n of k, nth instant DFT is depending on the previous instant DFT, and subtracting the oldest sample and adding the sample which is coming in xn, and the phase adjustment of Wm for k. For k equal to 0, what happens, this bin, we can see this purely the current k equal to 0 means that DC bin. For DC bin, xn 0 equal to xn minus 1 of which is 0, that is previous instant kth bin, that is 0th bin, and subtraction and addition. So this doesn't involve any twiddle factor in the calculation. Okay, so that's clear that the twiddle factor can be avoided simply if we push any of the bin to 0th bin, DC bin. So computation of this successive samples is only the current the sample, what was the previous sample window, and up to n what should be the samples. So just addition of these samples, it is just a summation of input samples only for the DC bin. When this considering the m length of the window. So if we take them WMK, that is absence, make this stable. So that won't be moving, just adding the number samples which are coming in would give the kth bin 0, that is 0th bin output. So using the modulation property to make it more and more that is stable, to avoid R in that, the shift in the frequency bin of interest, actually whatever the bin, kth bin we are interested in, shift that bin to 0th bin. So how are we going to do that? So xn 0, that is a previous instant one, and modulating using the modulation property, if we shift this n minus m, then that needs to be multiplied with the frequency. This is the modulation property WMK m minus m. You can see the shift over here in the frequency shift. Then xn, similarly the modulation property xm k into m. Okay. So this shift, which can have the shifting a signal in time that we had seen in the DFT example, also results in phase shift in the frequency domain e power j 2 pi k, and when the frequency x of k into the phase shift what should be there in the frequency domain. But when we use the modulation property here, multiplying with the signal with complex exponential in time, so it's not shifting. So it is a complex exponential signal to be multiplied in to x of n. Okay, if this is x of n minus m and this is multiplied over here, the complex signal, then that should be a result in a shift in the frequency domain. So this would be get shifted after so instead of shifting the signal, shifting property that we had seen in the DFT, if you multiply this xn minus m, that shift, and multiply that with the w suffix m minus km, wm minus km minus m. So that is the modulation property. If this multiplication of complex number results in shift in the bin x of k minus k naught, whatever the bin index should be. So use this modulation property. So this is reduced to now wm minus km, and here wm minus k into minus m, that is we have also seen in the previous case wm, this is plus m, that would become 1. Okay, so this is reduced to only xn minus m and x of n. Okay, so this is multiplying with the complex exponential. So results in the 0th bin has this, and if we want 0th bin output would be in the recursive equation is this, but if we want to take any of the kth bin output, okay, so this is 0th bin output. So if we want to do the same thing for the kth bin output, then x and k should be simply use this xn 0, and this modulation property again needs to x suffix m k m plus 1 should be used. So x suffix m k m here is the instant. Here this instant is different from this instant. Okay, m plus 1 to be multiplied. So this can be any frequency bin can be shifted to the DC bin. So that's the idea of avoiding this Tudel factor, which causes the instability in calculation. So any kth bin, this can be the instant I am showing it here, e power j 2 pi k n plus 1, that is m plus 1 which we had written by n into x0 of n. So the diagram results in this way. So first, that is n minus n, xn input, delayed n instance. So this the comb filter. Here we have this, or this xn minus m, and then we have this modulation signal getting generated, e power minus j 2 pi k n is this, and e power j 2 pi k n, this is multiplied by 1, so is this e power j 2 pi k by n. So when the realization, that would be written like minus and minus, so this is given as minus j. So e power j 2 pi k n, this by n, and e power j 2 pi k by n. So this is an instantaneous signal cos 2 pi k n by n minus j sin 2 pi k n by n, but this is a constant e power j minus j 2 pi k n by n. So delayed over here, and this is the part in which this x of n, that is kth bin, 0th bin, is delayed to accumulate. Here is this. Okay, so if you take the z transform of it, it will be z minus 1 into x sub 0. So that's the outcome of this particular integrator. And then we have this conjugate here, minus minus would be getting is e power j 2 pi k n plus 1 by n, same. Okay, the delayed and multiplied over here because we have this plus 1, so that would be taking it, and here if we rearrange this equation, you will get this. So up to up to this portion, that is, we can say, so from here to here, it is only the 0th bin, the green one, and if we add the remaining portions to shift the 0th bin output to the kth bin, that is multiplying this with 0th bin to 2 pi k n by n with to the xk n. So this is the kth bin mSDFT structure, which makes the twiddle factor free, that coming in the integration part and then accumulating the amplitudes or the error, amplitude and phase errors. So the simulated diagram of this mSDFT input, I like to give the input, fundamental and the second harmonic. We have this cos 2 pi k n by n minus j sin 2 pi k n by n. Also the constant e power j, that is e power j 2 pi k by n, is generated and delayed and multiplied over here. This portion is giving the comb filter, and the integrator part, here you get the 0th bin, and conjugate of it, take the conjugate and multiply over it. Here you get the kth bin as a complex number. This complex number, instantaneous complex number you would get. So separate them as real and imaginary and plot them here. So because we have this cos and sine instantaneous output, this should be known. So for this also fs needs to be f into n, because we are extracting the fundamental from this signal. So the case of the output, we can see the output, there won't be any difference in that output. The input, this is input, and here is the sinusoidal signal, and the cosine, in phase and quadrature component are extracted over here. So the fundamental can be extracted for k equal to 1. We can also change it for k equal to 2. So the multiplication and additions can be made different in the mSDFT case. The modulated SDFT uses the modulation property of the SDFT and pushing all the what are the bins being required to the TC bin and compute the SDFT. So we have seen the DFT case, and then how to use the shifting property of the DFT. That is, if the signal is shifted, time shifted, and what should be its DFT. So using that, one sample advancing every time. So how to use the previous instant DFT to compute the current instant DFT, we had seen through the sliding DFT. And this sliding DFT variance used to reduce the computational complexity, one, and then reduce the instability problem in the SDFT, looking at SDFT as a tuned filter which can extract the fundamental or second harmonic which are present in the signal by removing the harmonics and the noise as well. Can very well consider that as a tuned filter. So the variance, one we'll also see the variance of SDFT, which are, one is mSDFT and the H hopping DFT and modulated hopping DFT, and we will do the comparison of the complex multiplication and additions in this, and using this simulated diagrams in the Simulink, use these diagrams in the Ultra DSP builder and simulate them, and then we will show you that how this DSP builder thing can help you to code them generate the VHDL or Verilog codes and dump them into the FPGA for real-time implementation. Thank you.